Here we are going to solve this frame structure using direct stiffness method. Here you can see this frame element is consists of two members and area for both the element is constant. Young modulus is also constant. Moment of inertia is also constant for the both elements. Here, what you do, you have to find the deflection, or other way, you can deflected shape, as well as your bending diagram. Before going to the solution of this problem, first thing you should come in your mind that how you should keep the numbering. How you should go for node numbering, which element you should consider as the first element, which element you should consider the second element. The general answer is that you can choose any element as a first element, any element as a second element. Thing is that you should be consistent enough. You should be consistent enough. Okay. Now, whenever you are saying this is a first element, this is second element, and the nodal connectivity you should maintain always. Okay. So, what you have to do, you have to first identify what is the global node numbering. Okay. So here you can see I have given node numbering. This is node 1, this is node 2, and this is node 3. And I consider this is first element, this is second element. Other way, for this case, you can see I consider this is the first element and this is the second element. And node numbering here 1, 2, 3. Okay. Now what I'll do, I will always maintain the global node numbering. Okay. So here I consider this is the node number 1, 2, 3. Okay, global numbering. And whenever we'll try to obtain our local stiffness matrix. Okay, that time you should be careful enough to consider which is your node 1, local node 1, and which is a local node 2. For example, if this is your first element, okay, so global numbering, node numbering is 2 and 3, and local numbering should be 1 and 2 like this, or 1 and 2 like this. If this is your node 1 and this is your node 2, then the theta here for this case should be 180 degree. If this is your node 1 and this is node 2, then theta is 0 degree. Okay. Now, what we did, we consider this element as the first element, and our global node numbering is 2 and 3, and local node numbering we consider 1 and 2. Now, when I say this is our global node number 2 and the 3, local number 1 and the 2, then if we obtain the stiffness matrix for the element 1, we have to give local degree freedom 1, 2, 3, 4, 5, 6, and global degree freedom we have to identify here like this 4, 5, 6, 7, 8, 9. Whatever the component coming in 1, 1, local 1, 1, that should go to the global 4, 4. Right? Whatever the component will come here as the local 1, 1, that should go to the global 4, 4. Similarly, what other component will come here as your 2, 1, that should go to your 5, 4. So the main thing here is that you have to be consistent with your global node numbering, or other way, global degree freedom. And it should, the main thing is that you should identify the global node number, or other way you can say global degree freedom, and you should be consistent throughout this problem. Whenever you're solving one particular problem, you should maintain global node numbering and local node numbering, and it should be consistent throughout the problem. Okay, so thing is that we can assume any node numbering. You can choose global node numbering as a 1, 2, 3 like this, or 1, 2, 3 like this. We can choose this is node 1. You can choose this is element 1, this is element 2. or you can choose this is element 2, this is element 1. The thing is that we can choose any one, but you should be consistent enough throughout the problem. Okay, for this present example, what I did, I consider this is our element 1 and this is our element 2, and I consider this is node 1, node 2, and node 3. This is corresponding to global node 1, global node 2, and global node 3. So I have already identified what is your global degree freedom. So here 1, 2, 3. Okay, degree freedom 1, 2, 3. Here degree freedom 4, 5, 6, 7, 8, 9. Okay, now once we obtain global stiffness matrix, that time what I'm going to do, I'm going to apply the boundary conditions corresponding to this degree freedom and this degree, and then we're going to solve it. Okay, so let us see how we can obtain our local stiffness matrix and how we can apply our transformation rule. So here we are going to see how we can obtain our local stiffness matrix and then how we can apply the transformation rule to obtain our local stiffness matrix according to our global axis system. Okay, so here when you are here, what I am going to do, I am going to consider this is our element 1 and this is our element 2. Okay. Now, if you consider this is your element 1 and this is element 2, so here you can see element 2 is lying horizontally and theta is equal to 0 degrees. So for this case, you do not need to apply any transformation rule. Okay, but for the element 1, here you can see if you consider this is your local node 1, okay, and this is your local node 2. In that case, this is oriented at the angle theta is equal to plus 90 degrees. Okay. Other way also is true. If you consider this is your local node 1 and this is your local node 2, then you have to consider this theta as your minus 90 degree, or this way you can consider theta is equal to 270 degree. Okay. Now, if you consider another node numbering systems, if you consider another element numbering systems, if you consider this is your element 1, this is element 2, okay, and if you consider that this is a local node numbering 1 and 2, in that case, again, theta should be 190 degree for this case. Okay, and now if you consider this is your node 1 and this is your node 2, local node 1 and local node 2, and then this theta will be your minus 90 degree or plus 270 degree. Okay. This way you have to consider. So for this case, what I am going to do, I am going to consider this is node number 1, this is element number 1, and this is your element number 2. So I am considering this case. Okay. Now you know that we are going to solve this equation that F equal to K times U plus fixed and action. This fixed and action will develop if the forces acting within the element. Okay. If the force act in some nodal point, some particular degree of freedom, in that case, that force will come here. Okay. If the force is acting within the element, then due to that load, there will be fixed and action. Okay, that will develop in particular degree of freedom. Okay, and we have to identify it to get our displacement quantity. Okay. Now here, if we see this figure, that if 25 kilonewton force is acting here, then the fixed and action, in the fixed and action there will be reaction force as well as your moment. Okay. Now, if 25 kilonewton force is acting here, then this side there will be some reaction force. Okay, that value should be 1250 Newton, and this also Newton. Okay, and moment that will develop here, it will be here 18750 Newton meter. And here this anti-clockwise moment we consider as a positive, this is negative. Now similarly, for this case also, there will be vertical force acting here, there is some moment acting here and here. Okay, Now, if you consider that node B or node 2, okay, here we can see this side, that moment is acting clockwise, and this side moment is acting anti-clockwise. Okay, so here we have to consider both the moment to get our resultant moment. Right? And the forces here, you can see this is your force acting in the x direction, this force is acting in the y direction, so that are independent. Okay, so here you have to consider both the moment acting, okay, and you have to find our resultant moment acting in particular degree freedom. Okay, here in the 6th degree freedom, you can say this negative moment and this is positive moment is acting there. So resultant moment would be some positive moment value. Okay, that we are going to see while solving the problem. Okay. Okay. Now here, what we are going to do, we are going to consider this is our element 2. Okay, our horizontal element. First the horizontal element, and then we can consider the vertical element. Okay. Other way you also can do, you can consider first this element and then you can consider this element. Okay. The reason behind to choose this horizontal element, because in this case you do not need to apply any transformation rule. Whatever the stiffness matrix we will get directly, we can substitute this stiffness matrix into our global stiffness matrix. The only thing is that you have to be consistent enough. You should be consistent enough while giving your local node numbering and your global node numbering. Okay. So for this case, already we have learned that element stiffness matrix for a frame element look like this. Okay. First degree is corresponding to axial degree freedom. Fourth degree again is corresponding to axial degree freedom. That first degree and fourth degree, whatever I am talking about, that is your local degree freedom. Okay. Or degree freedom corresponding to the local node numbering. This is your second, third, fourth, and the fifth. Okay. So if we give the value of A, E, and L, we can identify that value is coming 2.5 into 10 to the power 9. So A is here 0.05, and E is here 200 GP, so 200 into 10 to the power 9, okay, times divided by L. L is your, in this case, 4 meter. So here you are getting 2.5 10 to the power 9. Okay. A is here 105 meter square. E is here 200 GPa, so 200 you have to convert into Pascal. So here you can see all the unit we are considering as a Newton meter. So 200 GPa, that means 200 to the power 9 Pascal. Okay, so 1 Pascal that is equal to 1 Newton per meter square. Okay, 1 Newton per meter square. So if we multiply AE, if we calculate AE by L, you will get this value. Similarly, you can calculate other value also. So we obtain our local stiffness matrix, and this is our local degree of freedom. Okay, and if you see that global node numbering and correspond to the global degree freedom, you can observe that global degree freedom is 4, 5, 6, 7, 8, 9, which is corresponding to this node and this node. Okay, so we consider this is node 1 and this is node 2, local node 1, local node 2, and global numbering is 2 and 3. Okay, now here we can see that this element stiffness matrix directly we can place in our global matrix. Okay. Now, if you consider the vertical element, okay, what we need to do? We need to first identify the local stiffness matrix. So here, what we did, we initially calculate 0 rate corresponding to element stiffness matrix. corresponding to theta is equal to 0 degree. Okay. And then what we need to do, we need to, this is the KE1. Yeah. Okay. So here we obtain our this matrix corresponding to our local orientation. Okay, where we consider this is node 1 and this is node 2 and it is oriented horizontally, so theta will be 0 degree here. Okay. Now here you can see this element is oriented at an angle of theta is equal to 90 degree, and theta 90 degree is positive in nature because it is anti-clockwise rotation. What we need to do, we need to apply the transformation rule. Transformation rule says that T transpose KT, you will get our space matrix which is in our global coordinate system. Here K is your KE1, so T transpose KE1 and T, that will give you space matrix corresponding to global orientation. Okay, so here locally this was oriented like this. Okay, but actually the structure is actually the same element is oriented this direction. Okay, so here we need to convert local orientation or global orientation, and for that case we need to apply this rule. Okay, so here we can see that T, this transformation matrix look like this. This transformation matrix look like this. Your CSSC here third term is corresponding to identity. Okay, because third term is corresponding to our rotational degree freedom, and once the member rotate in some angle here, that rotation about the z axis, third axis is not going to change. The rotation about this axis is not going to change. So here should be 1. Okay. Now if we do this operation, T transpose KT, you can obtain the stiffness matrix which is corresponding to global orientation. Okay. So global orientation and global node numbering is two different things. Okay. Global node numbering we already identified 1, 2, and 3. Okay. We consider that orientation. So number 2, global orientation and local orientation is the same. So there is no need to apply any transformation rule here. But whenever we are considering the vertical element, whenever we are considering the vertical element, you can see that our global x-axis is like this. Okay, global axial direction, axial degree freedom is like this, x. Okay, but for this vertical element, axial degree freedom is like this. Okay, so if you want to be consistent, in that case, our local orientation need to change so that so that our axial degree freedom and our axial degree freedom and other degree freedom is consistent for the same problem. Okay, so here you can see this is the axial degree freedom. Okay, if we consider our member oriented in horizontal direction, so local orientation and global orientation are the same. But whenever the member is oriented vertically, so here you can see locally this was our x-axis, so corresponding to this is x-axis will come the axial degree freedom, x-axis which was corresponding to axial degree freedom, but here you can see y-axis is corresponding to axial degree freedom. So they need to apply one transformation rule so that our axial degree freedom and other degree freedom consistent for the problem. Okay. Okay, so here what we are going to do, we are going to calculate T transpose K1T. Okay, and if we do this calculation, we will get the element stiffness matrix which is corresponding to 1 element, first element, the global orientation. Okay, so if we do this operation T transpose KT, okay, so here you have to follow this rule. Okay, that here C11, okay, C11 is the multiplication of this row and of this column. Okay. Similarly, from top then C2 to, then you have to multiply in that second row with the first column. Like that you have to do for all the element here that you can obtain the same. Here also you have to do the same operation. First you have to multiply K into T. Whatever the component will come, that matrix will be multiplied with the T transpose. Okay, if we do this multiplication, we will get the element stiffness matrix for the one. Okay. Now here, if you consider the node numbering, okay, so here you can see this is our local node 1, this is our local node 2, and global node numbering also 1 and 2. So here 1, 2, 3, 4, 5, 6 should be the same as 1, 2, 3, 4, 5, 6. Okay. Now, whatever the matrix we get here, whatever the matrix we get here, we have to directly fill it there. Okay. 1 for the element 1. Okay. Stiffness matrix for the element 1. Now, here you just see that your local degree freedom 1, 2, 3, 4, 5, 6, and global degree freedom is 1, 2, 3, 4, 5, 6. Here you can see this is 1, 2, 3, 4, 5, 6. Okay, local numbering 1 node, local node 2, global node 1 and 2. Here, the local degree freedom 1, 2, 3, 4, 5, 6, and global degree freedom also 1, 2, 3, 4, 5, 6. Okay, so here this matrix it directly come and will fill up to 6 by 6. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So here 1, 2, 3, 4, 5, 6, 7, 8, 9. So here, so this much will fill by the trace matrix, the element 1. Okay. Now we consider element 2, so trace matrix for the element 2. Here you have to be careful because your local numbering and global node number are not the same. Okay, so here you can see local node 1 and this is local node 2, but global numbering is 2 and 3. Okay, so global degree freedom will be 4, 5, 6, 7, 8, 9, and local degree freedom will be 1, 2, 3, 4, 5, 6. So here we just see local numbering 1, 2, 3, 4, 5, 6, global numbering 4, 5, 6, 7, 8, 9. Our value which is coming here 1, 1 that will fill 4 by 4 of the global stiffness matrix. We find the 4, 4 element here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Here 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4 by 4 will be here this value. So here you can this one, this value plus this value will come here. Okay, since I'm writing in for 9 terms, we're not able to see the higher order term. Okay, so here it should be here 2.539 plus 133, 138. Then we have 89 like this. So this will look here. Okay. Similarly, at your 2, 1 value 0 here, so directly you can see we had 0. Now again we have 0 value. Okay. And this value is corresponding to 4, 1. The 4, 1 value that will add in our this is a 4, 5, 6, 7, 8, 9. Okay, that will go to our 7, 4. Okay, that 4, 1 of local 1 that will go to our 7, 4. So here you can see that value is coming as here 7, 4. Okay, initially we fill up to this much and next one. Okay, so the second student's matrix will come here. That, but you have to be careful while filling this matrix. While filling this matrix, so here you have to be consistent with your global degree freedom. Similarly, Here you can see that your 6, which is local 6 value, that will go to global 9, so that value is coming here. Okay, consider because this one, okay, this value here, 1, 4, that will go to your 1, 4 of local, that will go to your 4, 7 of the global. 4, 7. So here you have to find what is the 4, 7 here. 1, 2, 3, 4, 5, 6, 7, 4, 7, 5, 6, 7, 8, 9. That will go to your 4, 7. 4, then 7 here. Okay. So the local 1, 4, that will come to 4, 7. Local 4, 4, that will go to 7, 7. So here we have to find 7, 7. Here this is your 7, 7. Similarly, what do we do? We have to find the value here corresponding to local degree freedom that need to convert to global degree freedom, and we have to fill it here. Now, if we combine it, okay, then we will get our global stiffness matrix. And global stiffness matrix will look like this. So here we obtain our global stiffness matrix, and you are knowing that we are going to solve F, that is equal to KGU plus FEA. Here we do not have any nodal forces, so this value will be 0. The vector F vector will be 0 here. Okay. Next thing what to do, we have to find the fixed end action. Okay. So here the fixed end action that will come as a reaction force, as a reactive force, that will come as a reactive force. Okay, reactive in the sense F, that we are writing KU plus FEA. Okay, so if we take this in the left hand side, so F minus FEA will come. If this is your active force, which is acting there, and then fixed end action will come as a reactive force. Okay, and that we are writing, and that we are writing in the right hand side. Okay, and that we are writing in the right hand side. So now here we will try to find a fixed end action. Okay, fixed end action acting at each degree freedom. Okay, or you can say at each node, and then we will transfer it to the degree freedom. Okay. Okay, so now here what we're going to do, we are going to see what are the fixed end forces are coming in the nodes of this frame. Here we just see 25 kilonewton force acting there. Okay, so due to this force, here we will have this amount of reaction forces, and here the moment that will be your WL by 8 amount, that will be positive if it is acting anti-clockwise. Okay, all anti-clockwise we are considering as positive. Okay, positive. Clockwise movement as a negative. So if you calculate WL by 8, you will get that value. For the second element is 2000 Newton forces acting there. So here we will have this amount of reaction forces, and here we have WL by 8, that is acting anti-clockwise. It will be positive here, and this is negative here. Okay, now what we need to do, we need to write this all the fixed forces in a vector form. Okay, here we know this A vector will be 0 vector, okay, null vector, and here in the fixed end absent vector, okay, the force were fixed force. Writing here, you can see this was value coming 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, here you just see this value is minus 12500 because we are considering this side as a positive direction. Okay, and vertical force here 0, so this is 0, and this is positive value in the third degree freedom, so 18750. Similarly, in the fourth degree freedom, we have minus 2500, minus 12500, minus 12500, and at fifth degree freedom is corresponding to the vertical degree freedom. Okay, so it's coming to 5, 25,000 Newton force. at 6 degree freedom, which is possible rotation here, that value is coming from your minus 18750 plus 25. Okay. If we add these two, this will be 1 to this will be 6250. Okay. Now similarly in the 7 degree freedom, 7 degree is corresponding to our axial degree freedom, so we do not have any axial force, that is 0. 8 degree freedom is corresponding to this one. This value is 2500, and 9 degree freedom is corresponding to your rotation here, clockwise rotation 7, that is your minus 25,000. Okay, so this way we can obtain our 16 forces. Okay, now what we're going to do, we are going to apply boundary conditions into this equation, and we are going to solve this one. Okay, we'll apply boundary condition in the stiffness matrix as well as in the force vector. Okay, here what we're going to do, we are going to use row and the column elimination technique to solve it. Okay. Now, if you want to apply the boundary conditions, there is various way to apply the boundary conditions. One easy way is the elimination of the row and the column. Here you can see we have obtained our global stiffness matrix, that is size of 9 cross 9, and of that size, these degree freedom are restrained and these degree freedom are restrained. So 1, 2, 3, and 7, 8, 9 degree freedom are restrained. So what we're going to do, we're going to eliminate that particular row and the particular column. Okay, and here that particular row, particular column. At the end, we will observe that we have only this 3 degree freedom left, which is unconstant. Similarly, we also will have 3 degree freedom left, which is corresponding to unconstant degree freedom, and we are going to solve this three matrix to obtain our unknown value for this problem is here U4, U5, and U6. Another approach is that you add some extra stiffness on the restraint degree freedom, okay, and you try to solve that problem. So here, if you want to apply extra stiffness, what you need to do, you have to first identify what are the degree freedom are restraint, and you have to apply or you have to add some higher magnitude on that particular degree freedom. Okay, we have not with that particular degree freedom. That means we have to apply some higher stiffness on that diagonal term of the restraint degree freedom that will replicate your high stiffness or high rigidity on the particular degree freedom. For example, here, if you want to have high stiffness value, that means that will replicate your fixed boundary conditions. Here also, if you apply high stiffness value, that replicate your fixed boundary conditions. How you need to introduce high stiffness value? How we can introduce high stiffness value? Whatever the value is there, you add some value. Okay, for example, this value is coming in the range of 10 to the power 5, and add some value 1 to 10 to the power 10. Okay, so now if you add this type of high stiffness on the diagonal term of the restraint degree freedom, that will replicate your fixed boundary conditions. In that also you can solve. In that case, what is the benefit? In that case, what is that benefit? Here there is no need to apply your row and the column elimination technique. Whatever the stiffness matrix you get, that is stiffness matrix, you need to add some high stiffness value on the diagonal term only, and you can solve it. You will observe that we are getting almost close value for that solution. Okay, now this high stiffness value is very relative term. This high stiffness value is relative term, is very relative terms. You have to see what are the magnitude is coming in the diagonal terms. If the magnitude comes in the range of 10 or 100, then you can add 1000 value, that will replicate your additional stiffness. If that diagonal term comes in the range of 1000 or 10,000, in that case you have to apply some magnitude of your 100,000 like this. Okay, so this additional stiffness will come in terms of additional stiffness you need to apply, which is very relative in nature. Okay, you have to do some trial so that it replicate almost fixed boundary conditions. Because here, what I'm going to do, we are going to see row and column elimination technique. Here we are going to see row and the column elimination technique, and we are going to get the solution. Okay, so here you just see we have written this equation F, that is equal to Kg times U plus fixed and accent. We are writing the same equation here. Okay, and what we are going to do, we are going to eliminate the row and the particular column from our Stiffness matrix as well as from our force vector. So here we are going to eliminate first row and the first column from our Stiffness matrix and the force vector, as first degree freedom is constraint, first degree freedom is restraint, second degree also restraint, okay, and third degree also, second degree also restraint, third degree also restraint. Similarly, yes, 7th, 8th, 9th. Okay, 7th, 8th, 9th, we are going to eliminate. Okay, now if you eliminate, you will observe we are having only this value. Okay, if you take out this value, it will look like this. It will look like this. Okay, if you take out this value, it will look like this here. So here this F vector is 0 values. Here this is corresponding to FEA. That value here is coming here. This is your or Stiffness matrix after eliminating row and the column. Now you can see we have 3 by 3 matrix, okay, and we can directly inverse it in our calculator, and we can see Kg times U. There should be U. There should be U. There should be U. There should be U. Okay, plus this one. U plus this one. Okay, U plus this one. Okay, so here this is K, and there should be some U here, and this is plus this next one. Okay, so you will get this one. U factor will be also 3 plus 1. Okay, now if we use calculator, you can get the inverse of this 3 by 3 matrix, and if you multiply with this one, you get our unknown below U, that is equal to K inverse here times your fixed and accent. Okay, and we have some negative value here. What is comes on this side, left hand side here. So some negative there. So here we will get U vector. If we multiply this, okay, K inverse times force vector. Okay. Now, what I have discussed, that we have solved this equation, and while solving this equation, we get, while solving this equation, we observe that forces here is 0 because there is no nodal force is acting. And we have calculated the fixed and actions from the forces acting within the element. And then what we did, we basically take this force, that fixed and action on the left hand side, and we write Kg times U. Okay, and then we solve it. If we solve it, we will get Kg inverse times your fixed and action here. Okay, and once we do that, we'll get this value. Okay, so here what we did, here we apply the boundary conditions. Once we apply the boundary conditions, the size of our Kg matrix will be your 3 by 3, and this also will be 3 cross 1. Okay, and once we multiply these two value, we will get this dispersion quantity, and we can plot the dispersion quantity as follows. Here you can say this n was fixed, so here we will have 0 displacement and 0 slope. Here we are representing it a straight line. Here 0 slope means this will be straight line here, and then we are basically getting some deflection point. We are getting some deflection, and here we observe that this delta 4 is positive quantity, and this one is negative quantity, and slope also is negative. Getting okay, and to maintain the slope, that part, this frame element need to deflect like this, and here again we have 0 slope and 0 displacement. Okay, so we get the displacement quantity like this. Okay, now here you just see this quantity is 3 cross 1. Now if you want to write that actual displacement vector, initially which was 9 cross 1, so here we can see 1 2 3 4 5 6 7, 8, 9. So what we can do, we can write all these quantities 0, and we have here U4, U5, U6 has 0, 0, 0. So our displacement vector will look like this if we write that here 9 plus 1 size displacement vector. So this displacement vector will be 9 plus 1 because we have total 9 degree freedom. So we'll have total 9 plus 1 displacement vector. Okay. Now here, if we want to calculate, the reaction forces, then we need to solve this equation. Now, if we write that displacement quantity here, 9 cross 1 displacement quantity, okay, this displacement quantity, whatever the displacement will occur, that is equal to reaction forces in the support. Okay, so here we can write this is equal to Fi. Okay, so total reaction forces, that will develop in the support, that will be equal to forces developing due to deformations plus your fixed end action. So if you want to find reaction forces that is developing the support, that will be equal to forces developing due to the deformations and the fixed end action. So here you can say this end is fixed, this end is fixed. Whatever the displacement quantity is occurring here, okay, due to that, there will be some reaction forces at particular degree of freedom here and here. Okay. So here in this support, this are the restraint. So this will try to resist the deformation. So there will be some reaction forces. Here we do not have any support. So there will not be any reaction forces. Whatever the moment and the forces are acting there, that will lead to the deformations in this particular degree of freedom. Okay. Now, if you want to calculate the reaction forces, we have to see what are the forces occurring due to the deformation plus the fixed action already acting in the frame. Okay. So here what we're going to do, here we are going to solve this equation. Okay, that your F, that is equal to Kg times U and fixed action. So here the size of this Kg matrix will be 9 by 9, okay, without any boundary conditions. Okay, and this will be your 9 cross 1. The 9 cross 1 only will have U4, U5 and U6 some non-zero quantity. Okay, and rest of the value will be 0. U1, U2, U3, U7, U8, U9 all will be 0, and this value is already known to us. Okay, so if we multiply this two quantity and if we add with this fixed end action, we will get the reaction forces here. We will get the reaction forces here. Okay. Operate on 9 plus 9 size matrix size, and if we do this operation, we will observe that reaction forces on the 4, 5, 6 degree freedom are 0. Here, this is 0, this is 0, this is 0. Okay. We'll have the reaction forces on the 1, 2, and 3, and the 7, 8, and 9 degree freedom. Okay. So here we have to solve 9 by 9 size stiffness matrix. Okay. But you can shortcut it, since you know that in this degree freedom there will not be any reaction forces. You can delete that. You can delete that column. Okay, and you can operate with 6 plus 3 factor with 6 plus 1 factor here. Okay, so here you can see we are considering. Here you can see we are considering only 4th, 6th, 4th, 5th, and 6th column. Here we are considering only 4th, 5th, and the 6th column, which is corresponding to our non-zero values. Okay, and then we are multiplying with the displacement vector, and here we are trying to find how much force is developing due to the deformations, and here already we know how much fixed end action is acting here on that particular degree freedom. Okay, so here 1, 2, 3, 7, 8, 9. Okay, so if you add it, you can find what the reaction force is here. So here the difference is that initially in this case, we are considering 9 cross 9 vector, and then we realize we have 0 forces, not 4, 5, and 6 degree freedom. But if you're clever enough, then you can realize here there will not be any reaction force. In that case, you can reduce the matrix size and you can operate on it, and we can find the reaction forces corresponding to the first degree freedom, second degree freedom, third degree freedom, 7th, 8th, and 9th degree freedom. Okay. So here you just see we are getting some value. So this is corresponding to our x direction, reaction forces in the x direction. So here this is a negative value, so we are representing in this direction. Second degree freedom, it is positive value, so we are writing it in upward side, and this is corresponding to moment. It was the third degree freedom, so here it is positive value, so we are considering here as your anti-clockwise moment. Okay, and we have 0 value here on the 7th, 8th, and 9th degree freedom. So here you can see this is negative value, so it is acting this side. This is positive value, writing it in upward side, and here this is negative moment, so we are representing it clockwise moment here. Okay. Now here you can see that all the unknown forces, all the forces are known now. Okay, all the unknown forces we have evaluated, and all the dispersion quantity is known to us. So now we can say this is our determinate problem. Okay. So here this is our determinate structure. Okay. Now since it is a determinate structure, then it is easy for us to draw our shear force on the bending moment diagram. So here you just see if you want to plot the shear force diagram, so we are writing it this side here. So this value is corresponding to this one. Okay, this will be minus sign here. Okay. And then we do not have any forces here in this case. So here this will be straight. Okay, this same shear force will continue here. Now here we have 25 kilonewton force. So if we add with this one, we'll get this value. Okay, and again we'll go like this. Okay, now here you can see this force is acting here. Okay, so basically this force here, you can say this force same thing is acting here. So this side will come to 0 here. Okay, now if you consider second, now if you consider this element, so here we just see we have these forces acting here. So this force also will act here. We are representing here. Okay, and then it will continue like this, and here we have 50 force. Okay, so if we minus with this value, if we minus here, this value minus 50 here, we will get this one, and it will continue like this, and here you just see we have this much force is acting here, so 0. So this is our shear force diagram. Okay, now you see our bending moment diagram. So bending moment diagram here, what we are doing, we are representing this side as a positive side. Okay, and this value is positive moment, and here you want to see how much moment is acting there, and what you have to do, you have to see how much moment is acting there, and what to do, you have to calculate the moment at this particular point. That moment will be the moment acting here. Okay, the moment acting here plus this force times this distance. Okay, so again we have to see whether this moment is clockwise moment or anti-clockwise moment. So here these are clockwise moment, so here we have to use negative sign, and you will observe this moment is coming like this. Okay, now if you want to see how much moment is acting there, so we have to consider just below this point here. Okay, and we have to consider the moment here and these forces and this forces, and we have to calculate the moment at this particular point. Okay, if you do the calculation, you will observe you are getting the some positive value here. So here this is positive value, this is negative value, this is positive value. So our moment diagram will go like this. Okay. Now, if you want to find the moment for this element, what we do, we have to just consider some point here, and You have to see how much moment is acting there. So at this particular point, moment you can calculate by considering the moment acting here and these forces and these forces. Okay, so here we can find how much moment is acting here. Okay, so you can do this calculation and you can find how much moment is. Okay, that value will be 21183.9. 211. That moment will be 21183.9 Newton meter. Okay, and at this point, you can calculate a moment, and that value will be 25920.9. And already we know this value is negative. So now you can add it like this. Okay. So here you just see we do not have any reaction forces as this point is free. Okay. So there is no reaction forces. That means there is no axial force, no transverse force, no moment. Okay. So this value is coming 0 here. But while calculating, we observe there is some moment is acting there. Okay. Now here you can see the moment here, develop moment and the force is acting here, moment and the force is acting here, that is causing the deformations at this at this node. Okay, at this node. Okay. Now here we just see, but resultant moment for the resultant moment will be 0 here. You can see just below this line. Okay, or if we draw, if we extend it like this, if we extend it like this, so here in this point, okay, here you can write this is A. Okay, so here before to the joint, that moment is positive, and after this joint, moment is negative. So that value are same. Okay, value are almost same. So at this point, resultant moment is 0. So there will not be any reaction forces. Okay, this side positive and this side negative. So resultant moment is 0. So there will not be any reaction forces. Okay, so here what we have learned? Here we have learned that we have to solve this equation to get our displacement quantity. Once we got the displacement quantity, using our equilibrium principle, we apply the compatibility conditions by placing the obtained value by placing the displacement quantity on this equation. Okay, so by solving that by applying the compatibility conditions, we are calculating the reaction forces. Okay, so once we get the reaction forces and displacement quantity, we get the displacement quantity, we can say that the structure is determined structure now. And once the structure is determined, it is easy to draw our and the bending moment diagram, and we can draw the shear force and the bending moment diagram like this. I hope you get some idea. Thank you.